So today I'm gonna represent my group to present the presentations about the applications of integration. So first of all, that our group name is Calculus is Fun, and move on. So let's talk about our group members. So first of all is Nguyen, Lê Nhân Văn, and finally is Bui Hoang Nhan. And each member has their own roles. So for Hưng, he will compose the PowerPoint content and presentations and do the PowerPoint.
So my name is Nguyen. Mm, my role in the group is making videos and come up with the content ideas.
And finally, Nhân, also me, is presenting and collecting pictures. So first of all, that we will talk about the birth history of integration application, about especially about geometry. So the first integral calculation was performed over 2,100 years ago by Archimedes, when he calculated the surface area and volume of several shapes, such as spheres, parabolas, and cone. Archimedes' method of calculation was very modern, even though at that time there was no concept about algebra, function, or even how to write decimal numbers. Move on, we will talk about the concepts and some formulas on application of integrals in the geometry. So the area of region bounded between the graphs of f and g with x is in the interval of a and b, we will have the formula such as like you guys can see on the slide. And talking about the volume of the solid obtained by rotating the dashes domain, the bounded between the graph of f and the x-axis, with x is in the interval of a and b about the x-axis. So in so volume equal the integral of between a and b and p with f square dx. And you guys need some note. So if we have a domain bounded between the graphs of two functions f and g with x in the a and b, then the volume of the solid obtained by rotating this domain about the x is equal to v equal to integral between a and b, and in the integral we will have p multiplied by the absolute f squared minus g squared dx. Similarly to the above situation, but this time we will rotate the domain of the y-axis, the volume of the solids will equal to the integral between a and b, and in the integral we will have 2 pi multiplied by the absolute x multiply fx and dx. And the note for this formula, so if we have a domain bounded between the graphs of two functions f and g with x between the interval of a and b, then the volume of the solid obtained by rotating this domain about the y-axis is v equal the integral between a and b to, and in the integral we will have 2 pi multiplied by the absolute of x multiplied by fx minus gx dx. And for a more clear and explicit imagination, you guys can see the formula on the slide. In the surface area of a surface obtained by rotating the graph of f with x in the interval of a and b about the x-axis, so we will have the area equal to the integral between a and b, and in the integral we will have 2 pi multiplied by the absolute of fx and multiplied by the square root of, and in the square root we will have 1 plus 1 at the derivative of fx square. And for the further imagination, you guys can watch this slide. And similar to the previous problem, but this time we will rotate the graph about the y-axis, not the x-axis at all. And the surface area of the obtained surface will equal to S equal to the integral between a and b, and in this we will have 2 pi multiplied by the absolute of only x and multiply with the square root of 1 at with the derivative of fx. And for calculating the curve of a function so let's just make an example like y equal fx, and with x is in the interval between a and b, so we will have the length of the function is equal to the integral between a and b, and in the integral we will have the square root of 1 and with the derivative of fx squared. So we will move on to some applications of integrals in geometry. So as you might know that before discovering the concept of integrals, the ancients used dredging algorithms to calculate the area of a circle, and it's very difficult and verbose to calculate. In fact, humans have been applying integral analysis for a long time in area measurement. Calculating the area of squares and rectangles is quite simple, but how to calculate the area of a circle? The ancients knew how to subdivide a circle into equal parts through slices passing through a center, then arrange them into a sawtooth shape to obtain a rectangular approximation, and thereby finding the formula for the area of a circle. The greater number of slices, the closer the rectangular area value is to the true value. Such methods are called exhaustive algorithms. So let's make it simpler to understand. I will explain it in our own words. So as you guys can see on the slide, so for initially that there is a circle with many slices, and they will set each slice into the sawtooth shape. Like it is absolutely similar to the shape on your right hand side. And first of all, that they don't even know what is the formula for calculating the circle. So they will divide the circle into many slices by drawing the lines through the center of the circle, and they will divide it into absolutely equal parts, and they will gathered it into a short shape, and by the shape they will make it maybe as much as possible. They will make it like the rectangular approximation, and by that they will calculate the area of the circle based on the short shape. However, today integral allows us to compute the circle with ease. So let's make an example. To calculate the area of a circle from the circle equation, x squared added with y squared equal the radius square, we will find a way to represent the over domain from the, the negative radius to the positive radius. For a semicircle lying on the axis y equals 0, like as you guys can see on the slide, so y equal f1x and equal the square root of radius square minus the x square, and the semicircle below the y equals 0, it will equal y equal f2x equal the minus of square root radius square minus the x square. So eventually that the area of the circle will be calculated through the integral formula of the function, and double due to the axis symmetry. Integral is one of the mathematical invention of the century, and it makes it easier for us to study in many areas such as calculating, measuring the velocity, area and volume, and etc.
Thanks for watching.